Welcome to this explainer. You know, we often picture AI and machine learning as this realm of absolute perfect precision. But the real world, it's messy. It's not perfect at all. AI isn't really about pinpoint precision. It's about navigating a chaotic, noisy world. Think of it like a detective's journey, just trying to pull a thread of truth out of all that noise.
So let's dive right into the big question we're tackling today. How does a machine learning model actually know when it's unsure? The stakes here are incredibly high. If a model is just blindly guessing in a world full of imperfect data, well, that's just dangerous. We don't just want a prediction. We want to know exactly how unsure the model is about that prediction.
To keep things on track, here's our game plan. We'll look at the problem with noise, dive into probability as the language of uncertainty, reimagine models as probability distributions, talk about updating beliefs with Bayes, visualize this predictive confidence, and finally, wrap up with why this uncertainty actually matters.
Section 1. The problem with noise. The messy reality of data. Let's go ahead and debunk the myth of the flawless algorithm right now. The real-world data we feed these systems is full of noisy observations that are just masking the true signal.
Take a classic linear regression model. What it does is try to draw a perfectly precise, rigid line straight through a bunch of scattered data points. It's desperately trying to find a pattern, but it's completely ignoring the massive uncertainty around all those scattered dots. It acts like it has the exact truth, even though the data is literally all over the place.
Moving to Section 2. Probability, the language of uncertainty. To find the truth without getting overly cocky, our AI detective needs a better tool. We need a way to mathematically talk about all this messiness.
And that brings us to probability theory. This is the secret language that lets models formally quantify noise. Instead of just throwing a dart at a board, probability theory gives the model a mathematical framework to essentially say, hey, based on this scattered data, I'm highly confident the answer is in this narrow range, and way less confident it's outside of it. It's the exact mathematical language needed for a model to quantify noise and state its exact level of predictive certainty.
Now, inside machine learning, there are two main ways to interpret this. First, you have the frequentist approach, which looks at relative frequencies. But honestly, that technically requires infinite data to be perfectly precise. The Bayesian approach, on the other hand, that is fascinating. It allows the model to state its exact degree of belief right here, right now, based strictly on the information it currently has. It treats probability as a measurable, subjective degree of uncertainty.
Section 3. Models as probability distributions. Armed with this mathematical language, we can totally shift our perspective. We can move from seeing predictors as those rigid, inflexible lines to viewing them as dynamic probability distributions.
Think back to that rigid line we talked about a minute ago. Sure, it spits out a prediction, mapping an input to an output, but it completely hides how confident or how totally ignorant the model actually is. If a brand new piece of data lands way out in left field, this rigid model is completely clueless about its own potential for being wrong.
But here is the real aha moment. What if we replace that rigid, single-point guess with a flexible, bell-shaped curve, a Gaussian distribution? Instead of a single fixed point, the model now outputs an entire probability distribution. It's basically saying, all right, here's my best guess right in the middle, but based on the noise, here is the statistical range of where the true answer most likely falls. To understand how a model actually learns to build this curve, we need to remember the three distinct phases in machine learning: prediction, training, and hyperparameter tuning. It's during that middle phase, the training phase, where our model is busy estimating these crucial parameters of uncertainty. The whole goal of learning is to dial in the model so it performs well on data it hasn't even encountered yet.
That takes us to Section 4, updating beliefs with Bayes. So how does our detective model actually learn over time? How does it actively update its confidence bounds when entirely new clues show up? Well, the answer is Bayes' theorem. You can think of it as the ultimate deduction method. You start off with a prior baseline of knowledge. Then, boom, new data arrives. Bayes' theorem gives you the exact mathematical formula to blend that old knowledge with the brand new clues. This refines your certainty into an updated belief, which we call a posterior distribution. You are literally updating your beliefs using math.
Let's look at Section 5, visualizing predictive confidence. What does all this actually look like when it comes together? Let's check out the visual climax of this journey, Bayesian linear regression in action.
And this brilliantly illustrates the payoff. Instead of that blind, rigid guess, we evolve into this beautiful cone of uncertainty. The model samples from a posterior distribution of plausible functions, mapping out predictive confidence bounds, say 67% or 95% certainty. Where there's a tight cluster of data in the middle, the cone is narrow. The model is highly confident. But towards the edges where there's no data, the cone flares way out. The model is mathematically admitting its ignorance.
Finally, Section 6, Why Uncertainty Matters. The absolute most crucial point here is understanding why all of this complex mathematical humility actually matters in the real world. I mean, why do we even care if a model knows it's unsure?
As the source material points out, this information is absolutely critical when we use these predictions in decision-making systems where bad decisions have massive consequences. Think about a self-driving car trying to decide if a dark shape up ahead is just a shadow or a pedestrian. An AI that evaluates the data and mathematically declares, I am only 67% confident this path is clear, is vastly safer and way more useful than an AI that just blindly guesses, assumes it's right, and hits the gas.
Which brings us to the ultimate question. If a machine learning model cannot mathematically quantify its own ignorance, can we ever truly trust its intelligence? I'll leave you with that thought about the true nature of reliability. Hopefully, it makes you want to look a little closer at the probabilistic foundations of the AI tools we rely on every single day.